confidence intervals. Really, this is just part one. I will have another video where we continue our discussion of confidence intervals. So what's been a recent goal of ours? Well, we've been doing point estimation of a parameter. This is where we estimate the actual value of the parameter. Today, and in part two, we will move into an interval estimate. So this is where we give an interval. It will contain our estimate and for which we believe the true parameter should lie. Well, the formulas for this theta sub L are lower bound of this interval, and theta sub U, the upper bound of this interval. These will be derived from the sampling distribution, and that was our very last lesson. So we're going to use a lot of what we just discussed. Okay, so given a parameter theta and some number alpha between 0 and 1, we will construct a 100 times 1 minus alpha percent confidence interval for this parameter theta, and we construct it from a random sample. Okay, here's the idea. You notice I have these magenta stars. This is really what you want to think about in terms of the interpretation of a confidence interval. If we sample the distribution repeatedly and constructed a confidence interval for each sample, we expect the true value of the parameter to lie in the interval 100 times 1 minus alpha percent of the time. This is what, well, I already have stars around it, but we can put an extra emphasis here. Okay, so part one, that's the video we are watching right now. Throughout this, I'm going to assume x1 through xn is a random sample from a normal distribution with mean mu, standard deviation sigma. And moreover, in part one, we're going to be creating confidence intervals for the mean, mu. So first, in this video, I have this assumption that the standard deviation sigma is known. Okay, so from the last lesson, we know this random variable where you take x bar, this is the mean of our random sample, minus mu divided by this known standard deviation sigma over the square root of n. This is a standard normal random variable, so it's distributed as n of 0, 1. Well, what are we looking at? This is the probability density function for this standard normal distribution. So how can we define a 100 times 1 minus alpha confidence interval? What we want is, in here, we want area to be 1 minus alpha. And the way I have this, that means that up here or down here, each of these tails, the area is alpha over 2. Down here, area is alpha over 2. All of this adds up to 1. Alpha over 2 plus alpha over 2 plus 1 minus alpha, it gives us 1, total area under the curve. We define this confidence interval for our unknown parameter mu, and we require exactly this. This area we know is probability. So we want the probability. Right here would be little a, right here would be little b. And then here is my random variable, comes from the sampling distribution. Well, how would we do this? Okay, if we wanted in this picture where the area of the two tails match and are the same, this little a will be the alpha over 2 quantile, which I can write as z sub alpha over 2. What it means is exactly what we see in the picture. This would be z sub alpha over 2, that the area below is alpha over 2. And similarly, this b, which would be this here, is the 1 minus alpha over 2 quantile, which says this area down here is 1 minus alpha over 2. So I will write that as z 1 minus alpha over 2. Now there is symmetry to this beautiful standard normal curve. In particular, here's 0. And this number is positive. And this number is negative of that. So 1 minus alpha over 2. So I'm going to write this right now. So this z sub alpha over 2, this quantile, negative z sub 1 minus alpha over 2. All right, now let's use all of this to get our 1 minus alpha % confidence interval for the population mean mu. Here is what we had on the last page. This is an interval really for this random variable. Now, what we want for a confidence interval is an interval around this unknown parameter mu. So let's do some algebra. Let's see, first I'll multiply through by sigma divided by the square root of n. Ta-da! That's the magic of my iPad. Now at this point, we can subtract x bar everywhere. We have one more step to get an interval around mu, and that's multiply through by a -1. When we do this, though, the inequalities switch the other way. So here is this previous line. Now, multiply through by a -1. All of the signs will change. This becomes like this. Now we see, here is our confidence interval. So let's write it. Be 100 times 1 minus alpha % confidence interval for this mu. Well, here's this lower bound that we talked about on the first page, theta sub L. You take x bar minus z sub 1 minus alpha over 2 times sigma over the square root of n. And then here is this upper bound, theta sub u. We take x bar plus z sub 1 minus alpha over 2 times sigma over the square root of n. Now we see this confidence interval definitely contains the sample mean, x bar, as we expect. Okay, now how do we get this number? This is the 1 minus alpha over 2 quantile for the standard normal distribution. Well, the good news is that we could ask R. We have this Q norm, which gives a quantile. And you see I have this screenshot from R, where I asked for 0.9, 0.95, 0.975, and 0.995. Here's the output. Now, I have made a table. My table is rounded. Here are some possible 100 times 1 minus alpha %. Maybe 80%, 90%, 95, or 99. Maybe I will just say that these two, 95 and 99, these are pretty common. Let's look at one of these to make sense of this table. Well, here, 80%, this says that alpha is 0.2. So we would have 0.1 and 0.1 on each tail. And so this 1 minus alpha over 2 would be 0.9. And then you see the quantile given by R. Of course, I rounded it. And for example, 95%, well, the alpha is 0.05, which means we have 0.025 and 0.025 in each tail. This 1 minus alpha over 2 is 0.975. And then here is what we got from R for this quantile. So that is how to make sense of this table. Now let me take a screenshot of it so we can use it in our next example. All right, here is the screenshot just so we can work through this example. Suppose we have a random sample. We can see it's of size 15. From the normal distribution, the mean is unknown. Standard deviation, we're assuming is known, it's 2. And we know the sample mean, 3.12. We want to find the 95%, 90%, and 80% confidence intervals. This is for this mu, population mean. So what are we going to use out of this table? Well, 95, 90, and 80. These will be this multiplier, the z sub 1 minus alpha over 2. Okay, let's get started. Maybe we'll begin with the 95% confidence interval. The mean is 3.12. We will have plus or minus sigma, which is 2, divided by the square root of 15, times, well, this 1.96. Now, you could use R, you could use some other calculator to figure this out. We get 2.11 to 4.13. Now, what changes? Let's move to the 90% confidence interval. In fact, I will begin and just copy and paste. However, the only thing that changes is we use this, the z sub 1 minus alpha over 2. Here for 90%, alpha is 0.1. So 1 minus alpha over 2 is 0.95 right here. So this changes. We have 1.64. So my confidence interval, 2.27 to 3.97. Finally, for the 80% confidence interval, here my alpha is 0.2. The 1 minus alpha over 2 is 0.9, and that we get here. This quantile, we will use the multiplier 1.28. So the only thing that changes is this multiplier, 1.28. And we get, let's see, 2.46 to 3.78. So 2.46 to 3.78. You notice if I lower the percent, we get a more narrow interval. Let's see, what I'll do is take this off and then rearrange some things. Now we can more clearly see each confidence interval sort of separated from the others. Okay, so definition, this number, you take z sub 1 minus alpha over 2 times sigma over the square root of n. You notice this is the half length of this confidence interval. It's called the margin of error. So we have this sample mean, and we move in each direction by this margin of error to get our confidence interval. It has two parts. It has this multiplier, and it has the standard deviation of the sampling distribution of the sample mean. That's a lot to say. But this general structure applies to the inference of other quantities other than the population mean, some of which we will discuss in part 2 of the confidence intervals video, where the margin of error really has two components. It has a confidence multiplier that comes from the sampling distribution, and then it has a standard deviation of the estimator. Now, we can see from this example, if you want to reduce your margin of error, namely you want a more narrow confidence interval, because of these two parts, there's two things you could do. One would be to reduce your level of confidence, and we see that here. So 95%, then the 90% is more narrow, and then the 80% is even more narrow than that. The other thing to do, which we don't see in this example, but we could increase the sample size, and both of those are quite intuitive for reducing your margin of error. So far, our discussion of confidence intervals, we've had this symmetric. We have had X bar plus or minus L. This was our margin of error, but it doesn't have to be of this form. So in my picture, you notice the two tails have different areas, but what I would still require is that all of this blue has area 1 minus alpha. More specifically, suppose alpha 1 plus alpha 2 equals alpha. And these are two probabilities, say, so I need that both alpha 1 and alpha 2 are non-negative. Then I can create this interval. We take the sample mean plus z sub alpha 1 times sigma over the square root of n. That's the lower bound. And then the sample mean plus z sub 1 minus alpha 2 times sigma over the square root of n. That's the upper bound. This is a 100 times 1 minus alpha % confidence interval for the population mean mu. And the derivation of this is very similar to what we did just moments ago. Now, often we are interested in a lower bound or an upper bound for the population mean. And for this, we can use what's called a one-sided confidence interval. So here in this setup, either alpha 1 or alpha 2 would be 0. So here are the two one-sided confidence intervals for the mean mu. Now in this one, you notice this number here will be our lower bound. So this confidence interval gives a lower bound for the population mean mu. In fact, the lower bound is this number right here. And similarly, if we go from minus infinity up to this number, this confidence interval gives an upper bound for the population mean mu. And the upper bound is exactly right here. So let's do an example. We're back to our random sample, x1 through x15, from the normal distribution with some unknown mean, standard deviation 2. And the sample mean is 3.12. I've just written this z sub 0.95 so we can use it. It's just some extra information so we don't have to call R or go back and look at our table. We want to find the one-sided 95% confidence intervals for mu. Okay, let's take 3.12 plus sigma over the square root of n times 1.64. And then we will take 3.12 minus, because this is the 0.95 quantile for the standard normal distribution, and minus that will be the 0.05 quantile for the standard normal distribution. Okay, this number is 2.27. This number is 3.97. So what are my one-sided confidence intervals? Well, we have one that goes from 2.27 to positive infinity. And you see here is our lower bound for mu given by this one-sided confidence interval. And the other one goes from minus infinity to 3.97. Okay, maybe I will make this a little smaller and make a remark. So this confidence interval, one-sided, we had 0.05 area in the tail. Now, if we divided that in two, we have 0.05 area in each tail, that would be a two-sided 90% confidence interval. And this is my remark. So recall, if we went here, 2.27 to 3.97, this was our two-sided 90% confidence interval for mu. Fantastic. Well, now comes a fun question. Okay, suppose we do not know the standard deviation. We still have x1 through xn, a random sample from the normal distribution, and we want a confidence interval for the population mean, but we don't know this. Well, the answer, we use t intervals. This we discussed in the very last lesson where we discussed sampling distributions. So if you take x bar minus the mean divided by s over the square root of n, this is distributed as the t distribution with n minus 1 degrees of freedom. Here, s is the sample standard deviation. Now the good news, the t distribution, which we looked at a few graphs of the probability density functions last time, but the probability density function is symmetric. And so what this means is if you take t sub, say, alpha over 2 with n minus 1 degrees of freedom, this will equal negative t of 1 minus alpha over 2 with n minus 1 degrees of freedom. Okay, so what do we expect for a two-sided confidence interval for the mean? Well, it's going to look very much like our z intervals, but the difference is we're going to be using a multiplier or quantiles from the t distribution. So is this the answer? Absolutely not. What I've done is just copied and pasted. So what changes, as I mentioned, this will come from the t distribution, and then we do not know the population standard deviation. So we will put the sample standard deviation, and then this comes from the t distribution. Now I need to add, we are working with n minus 1 degrees of freedom. All right, this looks great. Similarly, the one-sided 100 times 1 minus alpha % confidence intervals. Okay, I am doing a lot of copying and pasting here to get this down. But they look very much like what we saw for the z intervals. As with the two-sided confidence interval, what changes is we have the sample standard deviation, and then we use the multiplier from the t distribution, that quantile. So let's do one example where we create some confidence intervals for a population mean mu. Here we do not know the population standard deviation. Okay, so we have a sample of size 9 from a normal distribution, mean mu, standard deviation sigma. We want to find the two-sided and one-sided 80% confidence intervals for the population mean mu. We are told the sample mean is 4.7. The sample standard deviation is 18.2. Okay, so here we're going to use the t distribution with 8 degrees of freedom. So let's go to R just for a moment to figure out the correct quantiles. If we look at the problem, we're looking for 80% confidence interval. So I'm going to need two different quantiles. First of all, for the two-sided, I will have 0.1 and 0.1. So I need the 0.9 quantile. The other one for the one-sided, well, I will need the 0.8 quantile. So we can ask R. Here they are. Here's the 0.8 and the 0.9. Let's write this down. T sub 0.8 with 8 degrees of freedom is about 0.89, and T sub 0.9 with 8 degrees of freedom, this is 1.40. I just moved them to the side. Now we are ready to get started. So let's do the two-sided first. What I need is 4.7 plus or minus, here's the sample standard deviation over, well, the square root of 9 which is 3, but I'll write it this way, and then times this one, 1.40. My interval is minus 3.8 to 13.2. For the one-sided confidence intervals, I use this multiplier. So let's take 0.89 and multiply here. Here I get 10.1, I get negative 0.7. And so this one-sided confidence interval goes minus infinity to 10.1, and the other is negative 0.7 to infinity. Let's close this part 1 video here. C intervals versus T intervals. Okay, almost always in data analysis, the population standard deviation sigma is not known. So in practice, we typically use T intervals. And we will use, just as we did in this example, we will use the sample standard deviation in our calculations. However, what's also the case is, and this is something we discussed in the last lesson, as n grows without bound, the t distribution with n minus 1 degrees of freedom will approach the standard normal distribution. For large n, sometimes we will use the z multiplier. And the reason, well, there's no need to look up quantiles for different degrees of freedom when you're using a z multiplier. Well, thank you so much, class. We will continue our discussion of confidence intervals in part 2.